Now, I must say, I've got a confession to make. I came up with this title of my talk about 1.5 years ago, before the global pandemic and before I went on maternity leave. So I have to say, I don't actually, if you've come for some definitive answers on surface subsidence, then you might be a bit disappointed. But what I am going to show you is some hot off the press modelling results. And I suppose actually maybe in this, for this talk, it should actually be some cool modelling results that are hot off the press. So here we go. Now, I thought it'd be quite useful, because this is a virtual conference, to give you a little bit of a background about me, first of all. So there I am in an abandoned mine. And I used to work as a hydrogeologist, and I've always been interested in the flow of heat underground. And then I started working at the Coal Authority, and I became interested in mine water hydrogeology and how water flows through mines. And then the PhD opportunity came up to look at both heat and in mine workings. So I thought it was...
Fiona?
Yes?
Can we just, a few comments have popped up saying, can you start sharing the screen? I think we are viewing it, but we've got your notes on the side.
Oh, sorry.
So if you could just do the full screen.
Yeah, sorry about that.
No problems.
This is what happens when you practice and then you don't do what you practice. There we go. Is that better?
That is perfect.
Okay, thank you for that. Yes, now you can hopefully just see a big picture of me and not my notes as well. Yeah, so basically I'm currently at the Edinburgh University doing research into mine water heat schemes. And so what I'm going to talk to you about today is some thermal hydromechanical modelling. So basically what that looks at is looking at the thermal response and also the water flow, and also how that impacts the rocks. So how does it cause the rocks to change or deform? I'm going to talk to you about 2 models today. The first one is going to be where I basically change the water level, and the second one is going to be about injecting heat. And I just want to say here, I've got 3, my project is supported by a NERC studentship, which is through the Edinburgh University E3 DTP, and I've also got an industrial partner, who's Quintessa, who helped me with some of my modelling. Now, I found the pitch of this talk quite difficult, because I know that I've got some serious geologists in the audience, but also a lot of people that maybe haven't done much geology and don't know much about mining. So hopefully everyone will get something out of the talk, but some of it might be a bit basic and some of it might go a bit over your head, but I'll try and hopefully cover everything. So what am I looking at then? So I'm focusing on these shallow systems, which a few people have talked about already, which are called pillar install systems, where basically these pillars of coal were left to hold the roof up before machinery was invented to take the whole process out with it safely. Now, these workings are generally shallower, and I'm interested in them because they're potentially easier to access because they're shallower and potentially cheaper in that respect. Now, what I'm sort of looking at is, say you extracted heat from these workings and then re-injected colder water, you could then use that same cold water, say in the summer, and use it for cooling. So in that respect, you would take the cold water out and re-inject hot water. And then you've got a cyclical change in both heat and temperature. And what I'm looking at is, if you're changing all this water level and the heat, are you then going to cause any pressure and temperature and problems that might impact your stalls and might cause them to fail, perhaps break or collapse? So my first model I'm going to talk about is my changing water level model, which you'll see I've got a little water drop here, so you'll know that's what I'm talking about. So as I said, I'm just modelling, I'm keeping it quite basic to begin with just 1 layer of workings. And the pillar installs are 1 metres thick. And the workings I've modelled, the top of the model is 50 metres below sea level, and the workings are about 70 metres below sea level. And the bottom water model is there. And my pillars are 12 metres wide and my stalls are 6 metres wide. Now, this kind of setup is based on reality. Obviously, all collieries have very different geometries. but I've gone for quite a conservative one to try and make sure that anything I do see isn't sort of an extreme value. And my model's fully saturated so that I can look at the water level changes. So my mesh then, what you do is, if you're doing any numerical modelling, you have to have a mesh for the calculations to be carried out upon. So what I've got is, I've got two different material properties. So I've got my coal pillars, which are in here. You can see them there. I've not meshed in the stalls because water doesn't have rock properties, so they've been unmeshed, they're not part of the model. And then everything else surrounding, I've got surrounding rock. Now that's between either, I've done different runs, but majority of it is the coal measures sandstones. And you'll see that I've increased the mesh density around these areas because these are areas of interest. I want to know what's happening around there. Now all models need boundaries to work. So what my first model is, like I said, it was changing water level. So my hydraulic boundaries are water levels increasing from -40 meters below sea level, which is just 10 meters above the top of the model. Then it goes up to 30, then 20. So I'm simulating rising mine water level. For my thermal boundaries, I've given them a geothermal gradient of 30 degrees per kilometre, which is roughly what Gareth was showing in his data. But obviously, you know, I've taken a kind of average of that. And then my mechanical properties. So this is what happens to the rock. So what I'm saying in the rock is that it can be squashed down and in, but it can't go outwards. So it can be squashed, but it can't go outwards, to give it a bit of boundaries. Right, and now I'm going to talk a little bit about rock mechanics, which might scare some people, but I'm going to try and keep it simple. But basically, if you're talking about rock failure and rock fracture, you need to have some sort of constituent model that can predict what failure is going to happen. So the model that I'm looking at is this Moore-Coulomb criteria. And this particular criteria expects that it looks at both the max and the minimal stress. So if we imagine our max stress is up and down and our minimal stress is horizontal, what it suggests is then that when the rock breaks, it breaks along the shear failure plane, causing a crack in the rock. And what you can do is, if you've got your stresses and you know your shear values, you can plot them up on this graph. So you've got your stresses along the bottom, and you've got your shear values up the side. And you get these things called the Moore-Coulomb circles. So this is your maximum stress, and that's your minimum stress, and this is your values in between. So you can do this for lots of different rock types, and you can look at them. But what's interesting is if you look at the failure envelope. So this line represents when the rock will fail, when the rock will achieve this shear failure plane. So if my blue circle touches my red line, it means that the rock has failed and it'll fracture. So what I'm interested in then, if you take a point on the circle and you look at the tangent to the point, you can then work out what is our factor of safety. So how close are we to failure from this rock? So what you really need to take from this slide is that we're looking at this thing called factor of safety. And if your factor of safety is less than 1, it means that the material has failed. And the closer you are to 1, the closer it is to failure. So the less stable it is. So there we go. That's a quick rundown of some rock mechanics. Okay, so some of my results then. Now, this is my conceptual, a kind of schematic of my model. The scale is correct horizontally, but it's not correct. It's not to scale vertically, just so I could fit some of my results in. Now, what we found, first of all, so this line here is about, so the top of my model is at 50, -50. This line is data from -55 meters. And the first thing to notice here is that the factor of safeties are really, really high. So we're not anywhere close to 1. And what's that telling me is that my model's not close to failure. And this is what I expect because I'm using average values for a lot of my parameters at this stage. And usually it's the extreme values which cause failure. So at this stage, I'm not kind of stressing my model too much. And then what we look at is that the pattern is quite important here. So if you kind of look above the stalls, this line here is a bit deeper than this one. So it's 10 meters deeper than the other one. And you'll see that it's showing a kind of more pronounced pattern. Now the scale is the same on the side. So you'll see that above the stalls in both of these, they're actually got the highest factor of safety. So that's showing that they're most stable above the stalls, and that's to do with arching of the materials. And then, oh, sorry, another thing on this one is that if you look, this line's a bit deeper, just 1 meter above the workings. And if you take the kind of lowest point of each of these lines, what you can notice is that the factor of safety of that is actually reducing. So when you're close to the top of the model, it's around 25. And as you get down, it's towards 5. So what that's telling me is that stability in my model is varying with depth the closer you get to the workings. And the lowest points here are right on the edges of my pillars. And so these could be areas of interest of where the model might fail first. So these could be areas of interest. So I wanted to just have a brief break from some rock mechanics, but just show you these are actual pillars that were established, that they were dug out. So these show the kind of size that you're looking at for your pillars. And what it shows you is that one of my first take-home messages really that stability in the rock system is not constant. And what I need to kind of look at is areas of potential failure need to be investigated further to try and work out which ones are going to fail first. Okay, so let's look at some other results. Well, if you look at our Moore Coulomb, we knew that it was a very stable model because I had a very high factor of safety. So if I was going to draw my failure envelope one here, it would be way off here. So what I've done is I just put an example failure envelope on. Now this purple line, again, that's my stress that side and my shear stress up here. Now this is for my first model of changing water level of a water level of 40 meters below sea level. So what happens if I change the water level? Well, if I change the water level by 10 meters, what you'll notice is that the green line has moved slightly to the left and it's got slightly smaller. So that's telling me that it's actually getting further away from the failure envelope. So this change of 10 meter has caused a stability change in the rock. So that's quite an interesting finding. Now these results were for sandstone. So what I also looked at was if we changed to look at limestone parameters. Now that first line is the same line as you saw on the previous slide for the 40 meters. And then if you look at the limestone, I changed the properties to limestone. If we look at the limestone, it's actually getting, for this particular rock properties, getting closer to this failure envelope. And so that's telling me that the rock's becoming less stable and it's getting closer to the failure envelope. So here's another picture of some pillar and stall workings. I think this was from near Newcastle and their 19th century workings. And again, my second take-home message really is that water level and rock properties impact stability. So what I need to try and find out is what pressure values and what rock properties cause most change in the factor of safety. And what if we start looking at changing water pressures and cycles? If you're looking at kind of storing energy and taking out and re-injecting it, you might have cyclical patterns of how does that impact the rock stability. So then my next model, I want to go through a few quick model results, but again, this is my water level changing model, and this is my boundary conditions that I talked about earlier. If we look at the thermal heat injection model now, what I've done is I've just kept the water level the same to try and simplify it a little bit. So I've taken out the other two steps. I've just got the water level 20 meters above the top of the model. And now what I'm doing is, because I'm just imitating as if you would inject heat into the different stalls. So this would be if you were imagining you were injecting heat straight into the stalls. Now, obviously in real life, these systems are in 3D. So you would inject it into one point and the heat would travel around. But just as a kind of first case scenario, I'm just assuming the same temperature is going to each stall. And what I've done is I've done these cycles. So this would be a heating and a cooling cycle of abstracting heat and re-injecting heat. So say we injected 50 degrees in the first step, the next step we would then inject 20 and then 15 and 20 to give this cyclical injection pattern. And then again, sorry, the mechanical properties are the same as they were before. So these are my results. So on my injection of temperature, the yellow values are higher temperature. So obviously around the stalls, you're getting very hot very hot temperature signals, and then obviously that reduces, and then you're getting this heat injection again, and then that reduces. Now, what I thought would be quite interesting to look at is the maximum stress that you get. So as I said, the pillar edges are quite important for rock stability. So if we look at the 50-degree model, you'll see that the maximum stress is highest around these pillar edges, around the edges of the stalls. You've got the highest pressure. And then again, you do have high pressure around here, but it's a different pattern on your 20-degree injection. So what this tells me is that the change in temperature is causing a change in the stress field in the rock material. So I know that I was billed as talking about surface subsidence, so I thought what I'd look at briefly is to show a bit of displacement. Now this line here is taken from the top of my model, and what you can see here, so what you're seeing here is this is horizontal distance throughout the model, and this is vertical displacement in millimeters. Now as you can see, the heat injection obviously causes a change in vertical displacement. The actual values I'm not that concerned about right now. What I'm actually interested in is the change. So what I'm looking at here is between a step of injection of 50 degrees and a step of change of injection of 20 degrees, I'm getting a change of displacement in about 2 millimeters. Now, what I need to do is compare that to hydromechanical models, to my water changing model, to see what causes most change. But if we put that into a bit of context, this 2 millimeters, this map here was created by Terra Motion, and they're looking at uplift and subsidence throughout the whole UK. I just focused on Scotland, but if you look here, annually there's 8 millimeters of uplift and minus 8 millimeters of subsidence every year. So the 2 millimeters could be quite insignificant. So the importance of that, it could be quite important. So really that's my third take-home message, that the vertical displacement due to heat injection is in the order of millimeters, which is quite interesting, quite interesting thing. Okay, so then to summarise, my take-home messages are that stability is not constant. Areas of potential failure in the rock model need to be investigated further. So things that might be important might be the depth of the workings, that obviously changes the stability, and it also changes horizontally. But equally, we need to think about workings that are not horizontal. They could be dipping, and also there could be interlocking workings above and below each other, which obviously will impact the values that we're seeing. The next take-home message is that water pressure and rock properties impact stability. So what are the most important factors, and how are these going to impact the rocks? If you're looking at a system that's injecting and abstracting heat, which is going to be important to stability? Are there any combinations that might cause failure? So if I start looking at extreme values of rock properties that it could be failure, we can then start thinking about risk maps and where these schemes might potentially cause subsidence. And then the third take-home message is that my vertical displacement due to heat injection is in the order of millimeters. And so what I need to look at is, how do cycles of heating and cooling impact this? Obviously, we know that the cycles that I've shown do show a change, but how important is this? And just thinking about what Gareth was talking about in the comms, is my research relevant? Well, back in the early 2000s, some crown holes appeared near the East Coast mainline in the southeast of Scotland. And basically what happened was they appeared next to the railway, and the cause, they think, of these crown holes was fluctuating and rising groundwater. And what happened was it caused a failure in the pillar and stall workings, which caused roof failure, which caused them to collapse, and it propagated upwards and caused these crown holes. Now, the impact of this was that there's a temporary speed limit on the railway, which resulted in delayed trains and timetable changes. And obviously the East Coast mainline is quite a busy one, which resulted in they had to divert 1.8 kilometres of track, and they had to totally rebuild the platform. And the overall cost of this was £56 million. Now, I'm not obviously saying that this is what's going to happen for mine water heat schemes, but if we're thinking from a comms point of view, if these schemes do have the potential to cause any subsidence, then we really need to understand the risks of that. I just wanted to brief this. Obviously, this is just if anyone doesn't know what a crown hole damage can do, this is a picture from the Coal Authority, which caused a crown hole caused some damage. I don't exactly know where it is, but yeah. So yeah, just to reiterate, I've got 3 take-home messages, and those are my contact details if you want to contact me. Thank you.